Okay. I don't know. Here in Brazil is good. In Rio is good. Good evening. I think in England, Europe, good evening. In America, I think it's good afternoon. In China, I don't know, good morning. In Australia, good morning. Doesn't matter. It's our pleasure to present my dear friend and colleague, Professor Andrew Harvey. We really we were sort of looking forward to have you all here in Rio. The weather is beautiful as it was in July when it was expected to have the conference. And today you have 36 centigrades just to make you feel you are enter the winter, we are sort of entering the summer. But I think the conference had to be virtual, and nothing we could do but accept the way. We did our best to have the conference in Rio, but it's been very well looked after, and it's going pretty well from in this new way of presenting a conference. I'll pass to Fernando, who's going to do sort of describe a little bit of my colleague.
Hello, everyone. Good afternoon, good evening, good morning. It's an honor for me to introduce Professor Harvey for the 2020 Arnold Zellner Memorial keynote address. Professor Harvey is Emeritus Professor of Econometrics in the Faculty of Economics, University of Cambridge, and a Fellow of the Corpus Christi College, the Econometrics Society. Prior to that, he was Professor of Econometrics at the London School of Economics and lecturer at the University of Kent. He has published over 100 articles in journals and edited volumes. He is the author of 2 textbooks, The Econometric Analysis of Time Series and Time Series Models, and 2 research monographies, Forecasting, Structural Time Series Model, and the Common Filter. His most recent book is a 2013 monography entitled Dynamic Models for Volatility and Half Tails. Everybody in the world of time series knows Professor Harvey. He was elected as a Fellow of the British Academy in 1999. He was one of the developers of the stamp package, and his research interests are in time series, and his non-research interests include football, opera, and hill walking. Professor Harvey has influenced many researchers and academics over the world in the last decades, including Professor Reinaldo, my PhD supervisor, that was his research fellow in LSE in 80s, studying stochastic cycles in time series. Thus, as Professor Reinaldo was my supervisor, I am part of Professor Harvey's offspring. Since my master, I studied structural time series model by his books and papers. I'm very honored to introduce Professor Andrew Harvey to this ISF plenary with a very hot topic, time series models for forecasting coronavirus. Please use the Q&A to post your questions and the chat for general comments. Thank you very much, Professor Harvey.
Thank you very much, Fernando. I'm going to, having said hello to everybody, I'm going to turn off the video because I think it will give me a better connection. And hopefully it won't turn off everything. Perhaps you can show the first slide. I'm afraid it seems to have frozen.
Just a minute.
Fernando, the slides were shared. Do you want to try it again?
Yeah.
There you go. The slides are up. Andrew, can you see them?
Can you see Andrew?
Yeah, I'm.
Your video is off.
Can you see the slide, Professor Harvey?
Can you hear me?
Yes, yes.
Oh, okay, good. I don't seem to be able to switch off the video.
We can hear you.
Video. Okay. I can't see the slides though.
Oh, I'm sharing my screen.
Oh, okay, hold on.
I guess you can turn off your camera.
Right, I'll try that. Okay, fantastic. Oh, I've lost it again. Yeah. Okay, I can see the screen, and can you hear me as well?
Yes, we can.
Fantastic. Okay, well, hello again, everybody. What you can see here is something that will be familiar, I think, to many people now. It's a plot of daily new cases of coronavirus. And this one is for Germany, but it's fairly typical of many countries. Now, what you can see there is the numbers are going up until the beginning of April. And at that point, we start to make forecasts. So the forecast is actually shown as the dashed line. And you can see that it's actually tracking the actual observations, which subsequently come rather well. So there's two features to the forecast. The first is that there's clearly a big daily effect. And that's partly because they didn't do lab tests at the weekends initially. But the other thing, the most important thing, is that it's going down. Now, the question is, how did we do this? How did we construct a class of time series models that are actually going to model these kind of observations? So next slide, please, Fernando. Okay, so we've developed a completely new class of time series models for predicting a variable which, when cumulated, is subject to an unknown saturation level. In other words, if you make the total, there is an upper bound. So in terms of an epidemic, it means that everybody's either had it or they've died. Which sounds a bit dramatic. That kind of setup comes up in a lot of disciplines. For example, if you're looking at sales of a new product, and there's quite a lot of literature on that, and that's been, the kind of thing that's sometimes been presented at forecasting conferences, but much more for new products, that kind of thing, rather than for epidemics. Now, the models we've constructed allow you to make nowcasts and forecasts of the daily number of cases or daily deaths, the growth rate, and also this instantaneous reproduction number R, which probably none of us had heard about in March, but we all know an awful lot about now. And what everybody in the world knows now is that if it's above 1, this is bad news. Okay, the models are classic time series models. Estimation is by maximum likelihood, and you can do the usual diagnostics. Next slide, please, Fernando. So these time series models are different to the kind of models that the epidemiologists have been using. They tend to be what are sometimes called semi-mechanistic Bayesian hierarchical models. In a way, they're a little bit like some of the macroeconomic models, like DSGE models. in that they're based on a set of equations which come from theory, and then those are simulated under various assumptions to see what might happen. But a lot of the assumptions that are going in there are really, you know, very big assumptions. Now, what we're doing is just building rather simple, initially, univariate time series models, just using the historical data. And these models are very transparent. I mean, you can see exactly what's going on, so the results can be reproduced. There's a nice article which describes those contrasts, which I give below. Okay, next slide, Fernando. Well, these are the papers. This is what kept me amused during lockdown in the UK. So the first paper, which sets out the basic ideas of the models, is this one, Harvey and Catterman, in the Harvard Data Science Review. Then there's another one which looks at R and explains how you can use these models to actually estimate R as an alternative way to what the epidemiologists are doing. And finally, there's a paper that's just come out as a National Institute of Economic Social Research discussion paper, which looks at how, when you look at several time series models, you can construct leading indicators, you can construct control groups, and you can make policy assessments. So I think that's all very potentially interesting and important. Next slide, please. So what do we model? Well, what we don't model is the cumulative total or the daily numbers of new cases or deaths. What we do is we end up modeling the logarithm of the growth rate. That's the growth rate of the cumulative series. And why do we do this? Well, the reason is we looked at growth curve theory. So growth curves are curves like logistic and Gompertz and so on. And that led us to consider taking the log of GT, that growth rate. And it indicated that that would follow a downward time trend. Now then, the important next step was to make that stochastic. So you make it into a true time series model. And the characteristic of time series models for non-stationary time series is that the trends are stochastic. And that's precisely what we do here. So next slide, please. So here you can see some very recent data. This is data I was looking at last week, and it's for new cases in Manchester. Well, Ronaldo at least will know they have a couple of famous football teams. Anyway, you can see that there's no way you would want to model this. You know, it looks pretty horrible as a time series. But if you look at the log of the growth rate, you can see that's a lot nicer. That looks as though it's going to be much more amenable to modeling, and indeed it is. It also tells you why you need a stochastic trend, because the trend goes down initially, it's going down fairly clearly and almost a linear trend, then it bottoms out, and then it starts to come up again with the second wave, which is something that most European countries are now experiencing. So next slide, please. So that's just univariate modeling. The multivariate time series modeling, I look at number examples. I derive the theory and then look at these examples. So for example, I say, in the early part of the year, Italy was ahead of the UK. It got coronavirus earlier. So could it have been used as a leading indicator for the UK? obviously that's not much use now, but if it turns out that it could, then we might be able to construct leading indicators in the future. You could also use the same technology to use new cases as a leading indicator for deaths and hospital admissions. Finally, what I look at is the interesting case of Sweden, which famously did not have a hard lockdown. And the question is, can we answer the question, what would have happened if they had had a hard lockdown like most other European countries? Okay, next slide. So this is the UK and Italy in the first half of the year. And you can see that the UK lags Italy, but it's not apparent from that how you would actually model the relationship between them. But as you can probably guess, what we're going to do is take the log of the growth rates, and then everything becomes very clear. However, that'll have to wait for a little while. So next slide, please. Well, no, I was wrong on that. Here it is. Here are the logs of the growth rates, and this is actually deaths in this case. And you can see that now the two series are moving along together. So this is the UK, this is Italy, and you can see this gap here is because the UK is lagging Italy. And we'll see later on we'll see why that comes about and how we can then construct a time series model for a leading indicator. So next slide. Okay, so we'll now look at some growth curve theory. What you've got here initially is a Gompertz growth curve. If you're not sure what a Gompertz growth curve is, just hold on, you'll get it in the next couple of slides. So the red line here is for the total number of cases or the total number of deaths. And it starts off and the growth rate gradually goes down until finally the growth rate is going to 0. And at that point, everybody's had it and the whole thing stops. Now, the line in green is what's called the incidence curve. So it's the derivative of this, and it's got its maximum there at the point of inflection. And it's this that's going to represent daily cases or daily deaths, or whatever it is that you're dealing with. The blue curve is another curve, but with a different parameter. Yeah, that's fine. Next one is fine. Okay. So this is a family of growth curves called generalized logistic. It includes, not surprisingly, logistic as a special case when kappa is equal to 1. And as you let kappa go to infinity, you get a curve called the Gompertz curve, which is actually widely used in a lot of disciplines. It's used for population growth and so on. And the Gompertz curve looks like that. So the mu bar is this saturation level. This is the upper level that you're going towards. The gamma here is a crucial parameter. It's the rate of progress parameter, and the gamma naughts are initial conditions. Okay, next slide. Whoops. Right, okay. So from those growth curves, you can get the logarithm of GT, which is the growth rate. And you can see here that it's equal to the log of the cumulative total plus a constant delta minus gamma t. So there's a downward sloping trend there. Okay, next slide. So we now want to convert that into an observational model. So we've got the cumulative total, big YT, and the daily amount, which is little yt, which of course is the change. Now, what you don't do is to model either the cumulative total or even yt, although there's quite a lot of work that went off in that direction. And if you look at books like the one by Panic, which is on nonlinear regression and has a whole, a couple of chapters on growth curve, that's what people have tend to do. But in time series, that's not what we do now. I mean, we have stochastic trends which are flexible and can move around. We don't use deterministic trends. In the early days of coronavirus, some of the US agencies tried to model with deterministic trends, and quite soon they found that it didn't work. Okay, next slide. Have we got the next one, Fernando? Right. Okay. So we end up with modeling either the log of y or the growth rate. And in fact, the growth rate is rather better. And that initially gives you a regression model, which is quite easy to estimate, but it's got the deterministic trend. And although we were using this initially, after about a month of lockdown, we realized that that was not flexible enough to pick up what was happening. Because of course, what's happening is that people are changing the behavior, and also governments are bringing in policies like social distancing and lockdown. And so it's really not behaving like a standard epidemic. And you got to use these time series methods to track how this trend is actually evolving over time. So next slide, please. So this is just the Gompertz curve. So this is when we put rho equals 1. And this is just saying what I've just said, that we've got to now make this model more flexible by changing this deterministic trend to a stochastic trend. Okay, next one. Just to show you that we're not just looking at coronavirus, this is the so-called Spanish flu. I don't know why the Spanish get blamed for this, but there you go. And this is in San Francisco, 1918. So again, this is the log of G, and you can see initially exponential growth, then it starts to go down. Okay, next slide. So stochastic trend. This will be familiar to some people and look completely new to others. But basically, what you've got is a level, delta, and a slope, gamma, and those are evolving over time. And they do so because they're hit by these disturbances here. Now, we're going to end up with a model in which that's knocked out. So it's a model which is called an integrated random walk, which means that the slope is a random walk, and it's the slope that feeds into the level, which feeds into the equation here. And the crucial thing that allows this slope to change over time is the signal noise ratio, Q. Now you can augment this model by adding other effects, and in particular, you might want to add day of the week effects. But you could also add in dummy variables for changes in policy, and that's something that we do later on. Okay, next slide. So the estimation of those things is by the Kalman filter and smoother. And the calculations I've done are in the stamp package of Koopman et al. But there's lots of packages for doing that, and actually it's not that difficult to program up a Kalman filter if you know what you're doing. So what I'm saying is the standard statistical methods for actually dealing with stochastic trends, and those are discussed in quite a lot of time series books. Next slide. Actually, you can drop that one out. Next one again. Now, having estimated the model, you can make forecasts, and there's some recursions for making the forecasts, and there's various formulae. But what the forecasts will tell you is that eventually, if your gamma is positive, you will go to a final level. So if you want, in the early part of the epidemic, we were making forecasts of what the total number of people was who would get it, and we're making forecasts of the total numbers of deaths. Okay, next one, please. And these are some of the forecasts of the movements in the daily number of cases. And this is right near the beginning, when we were still using generalized logistic models, and we'd only just started using the dynamic Gompertz model. So next one, please. Now, just as an aside, a lot of the epidemiologists argue that one should use a negative binomial distribution or even a Poisson distribution, because when you're dealing with numbers, so that of course is count data. But so we want to see if we can actually do that, and it turns out you can do it. You can use a negative binomial, and you can set up a model again with the level there following a downward trend. And next slide, please, Fernando. And that downward trend is driven by the conditional score. Now the conditional score and conditional score models is a whole way of modeling nonlinear time series, and there's been a lot of work done on that in the last 10 years. The ideas originated at the same time, actually, from me and from my former student, Simeon Koopman in Amsterdam. And if you go on to the next slide, we've got some, yeah, this is the 2013 book, and this is a list of all the score-driven papers that have been out recently. So if you want to find what's going on, that's it. And there's also a computer program called Time Series Lab, which you can actually download for free. It's being developed, this one by Rutger. So if you want to play around with it, do download that and give Rutger any feedback on using that. So it's a good way in which to learn about using dynamic conditional score or gas models. They're the same things. Okay, next slide. So this is an example. It's UK deaths, and it's showing predictions. You might think we're actually underestimating there, and that seemed to be the case. But then it turned out that they changed the data, because UK deaths were deaths if anybody had had coronavirus. So if they'd had coronavirus 2 months before, and then they got run over by a bus, they went down as a coronavirus death. And they then changed the data, so it was having had coronavirus in the last 28 days, and the result was that actually these numbers went down, and they were actually much closer to my model. So I was very pleased about that. Now, why don't we continue with the negative binomial? Well, the answer is the numbers are big. We're dealing with numbers in the several hundreds. So there's really no point in dealing with a negative binomial. You might as well use a log normal, which essentially is what we're doing with our Gaussian model for the log of the growth rate. Okay, we'll now move on and look at policy interventions. And what we wanted to do here was try to model the effect of the UK lockdown. So if you go on to the next slide, we modeled it by letting the dummy variables lie on a logistic curve. Next one, please. I'll go through them quite quickly. So we put in dummy variables, and if you look at the next slide, you'll see how it is. So this is the UK lockdown. So lockdown starts around here. This is the effect on the log of the growth rate. So it brings that level down, and then it continues on a new growth rate with a slightly steeper slope. So we're able to evaluate the effects of the lockdown. Later on, what I do is to see what would have happened if it had happened a week early. And then we consider tracking the second wave. Well, how might we do that? Well, we track it basically by looking at the filtered estimates of gamma and the growth rate, and those will give you the growth rate in the daily figures. Okay, next slide. Okay, so I'm just now summarizing that paper, that it's a new class of time series models. The basis of those models is these generalized logistic curves, and in particular the Gompertz curve. You let that time trend be time varying, you do that by state space models, Kalman filter. There's no problem in adding on additional components. Next slide. Yeah. And when you do the tracking of the series, you can also get an estimate out of R, and that's what I'm going to talk about for a few minutes now, how the estimates of R come about. So next slide. So you probably all know about the reproduction number now, which is supposed to be the number of people in the population who get infected by an individual. And that changes over time, and it changes in response to policies and so on. Now, what we say in this second paper, after discussing all sorts of methods for computing R, is basically don't bother with anything that's in epidemiology, because if you use our model, you can actually compute estimates of R directly from the output of that state space model. And there's different formulae that you can use. And the thing is, unlike lots of the ways in which this is calculated in epidemiology, what we're doing is quite transparent, and it can be subject to diagnostic tests. Okay, I'll go through the next few slides very quickly, Fernando. So yeah, we can move on from that, and move on to the next one. Yeah, and the next one. Okay, so this is back to Germany, and yeah, we'll look at the next slide, I think. which shows some estimates of R. So these are estimates of R, and this is the one from our model, and we're comparing with various other estimates, mainly the ones produced by the Robert Koch Institute in Germany. And one thing we're showing is that our estimates deal with the day of the week effect. Okay, next slide, please. Now, one thing we can do with the model is that not only can we estimate R and the GY, but we can also get out a sampling error. And that's very useful, because if you're going to say that R is 1.1, you want to know it's 1.1 plus or minus 0.2 or plus or minus 0.3 or something. You need some idea of sampling variability, and you get that from this model. Again, there's lots of ways of doing this in epidemiology, some of which I think are just simply wrong. Okay, next one. That's how to do it. Next slide. Yes, I'll miss this out as well. This is just showing you how the weights come about. So next one, move on. Yeah, move on. This is just discussing things. I think we'll move on a few slides now, Fernando, to get to. Yeah. Okay, these are more. Yeah. Okay, I'll just stop here a minute. So just wind up on R. Basically, we provide a method where you can get R as a byproduct of the calculations, but our calculations don't depend in any way on R, and they don't depend on some of the assumptions used in epidemiology. Okay, let me go on to the final paper now, and this is about leading indicators. So if you can just go back one. Yeah. So I'm going to look at leading indicators with these two examples. Some of the inspiration for this comes from a paper by myself and a student of mine, Stephen Teal, which is coming out in the Journal of Applied Econometrics. And basically that's on control groups. And it's really talking about synthetic control and saying that actually you should be doing it by time series methods. Now those time series methods are now something we're going to use here. So next slide, please. Okay, so these are some incidence Gompertz curves. So you can see that this one here, call this epidemic 1, is coming before epidemic 2. The curve here is epidemic 2, but it's got a higher saturation level. It may be that there's a bigger population. But let's look at what happens on the next slide, see what happens when we look at growth rates. Well, if we look at growth rates, we know the growth rates are a straight line. So let's plot them as on the next slide. And you can see that now what happens is that those two incidence curves, when you look at the log of the growth rate, now come out as parallel lines. So this is the leading one, and this is the other one is the one that comes after. And the point is that both of the lagging growth curves have got the same log G. That's why there's only 2 lines rather than 3 on the graph. And the lag is given by this. It's basically the difference between the 2 lines. Okay, next one. Now, the point about those is the epidemics are moving at the same rate, so the gamma's the same. If they're not moving at the same rate, you'd have this kind of setup. You see this one is evolving more slowly, and then the lines for the log Gs would not be parallel, and it would be much harder to actually do leading indicators. But I'm not sure that this situation is particularly relevant. I think it's less likely. Okay, next slide. So those were deterministic curves, and we're now going to make them stochastic. So we first of all just have a model like that, and then argue that you get the same curve even when the trends are stochastic, as long as there's what's called balanced growth. In other words, when we look at the difference between the leading series and the lagging series, that difference is stationary. So the things, they're always moving together. They're no longer straight lines because the trends are stochastic, but their difference is stationary. We can then add a lag structure to that. So we get a distributed lag model, and we can estimate that again with the restriction of balanced growth. So we want to do restricted least squares, which you can do as indicated here. Okay, next slide. If the series aren't on the same growth path, you can still get a model by introducing a stochastic trend here. And you can always test for that by looking at the residuals from the regression model. And that's what I'm talking about there. Okay, next one. We'll miss that one out. That's just how to make predictions. So back to daily deaths in Italy and the UK. You've seen that slide before. Next slide. That's just describing it. And again, you've seen this one before. It's the log of the growth rates. And hang up, just go, yeah, this one here. And now I've lagged Italy by 14 days, and you can see the two lines, or the two series, are more or less the same. One is superimposed on the other, and if I look at the difference, it's a stationary time series with a mean which is very close to 0. So we've got this very nice setup where we've got balanced growth. We've transformed the data to the log of the G's, and then the two time series are going along together, and you can use the leading one as a leading indicator for the lagging one. Okay, next one. Okay, and this just reports the model we fitted and the diagnostics. Okay, next one again. Right, the next example is in Florida, and I think I'll skip that. This is trying to predict deaths in Florida from new cases. And again, it's the same idea that there's a lag there. When we shift it, we get the two series moving together. You can see here, these are new cases, and the blue ones are deaths. As you see, it's complicated by this day of the week effect. And then the next few slides just show you that this actually works. So we'll move on quite quickly on those. Move on to the next one. And the next one. And that's just showing that it does actually forecast rather well. Okay, we'll miss this out too, because I'm running out of time, I think. Okay, this is the final section. And I want to look now at policy interventions. And I'm looking at two questions. First of all, what if lockdown in the UK had been a week earlier? And secondly, what if Sweden had had a full lockdown? So let's look briefly at how we might answer those questions using these time series models. Okay, so the UK went into full lockdown on March the 23rd. So what would have happened if it had gone in March the 16th? basically what we do is we shift the intervention forward a week. And if you just go on a couple of slides, Fernando, to the graph, we can see what's happening. Okay, stop here. So yeah, so this is what actually happened. And then if we shift it forward a week, we get the green line. And essentially from that, we can work out what the consequences of doing this rather than that were. And we can go on to the next slide to find out what the consequences were. This is just going through on the methodology. It's trying to estimate the total number of deaths, and the basic result is it probably increased the number of deaths by about 40%. So if the UK government had actually been a little quicker going to lockdown, they could have saved a lot of lives. Finally, we'll look at Sweden. Sweden's been very interesting. And as statisticians, we really like this because we like to have these experiments that people do with different policies. The question is then, Sweden only had a very soft lockdown, and what were the consequences? Now you might, when you look at data for some of the other Scandinavian countries like Finland and Denmark, the number of deaths is much lower than Sweden, but that can be quite misleading. So here we've got UK, Italy and Sweden. And Sweden there, the numbers are much smaller because it's a much smaller country. But when we take logs of the growth rate, which comes out on the next slide, I think, well, the one after that, yeah, this is the important one. So when we look at the log of the growth rates and we shift Italy by 14 days, so it's the same as the UK, what we see is something really interesting. Because what happens is until the end of, well, till round about midway through April, they're on the same growth path. Now, the UK goes into lockdown, as we know, on March the 23rd, but that takes some time to work itself through into deaths. I mean, it takes 2 or 3 weeks for deaths to follow from an infection. So you're not going to get an effect of the lockdown for a few weeks, in fact, until about here. Italy's the same because we've shifted it by 14 days. What happens to Sweden? Well, Sweden's initially on the same growth path, and then it starts to move off. And the difference between what you've got for the UK and Italy on this growth path and what you're getting for Sweden is the number of additional deaths you get in Sweden because they didn't go into full lockdown. So you're using the UK and Italy's control groups. Now, people might say, well, you know, Italy is nothing like Sweden. It's not not in Scandinavia. Why aren't you using Finland? Well, actually, this is irrelevant. It's the fact that it's on the same growth path that is actually the important thing. And next slide. If you look at the other Scandinavian countries, the numbers are actually very small. It's very difficult to make a comparison. So the overall conclusion we get, we can work this out, is that there were perhaps 40 to 45% more deaths than there might have been if there'd been a more stringent lockdown of the kind implemented in the UK and Italy. But on the other hand, they kept the pubs open, you know, so that was the benefit. And of course, it's better for the economy. Okay, I now talk a little bit more about Denmark and the other Scandinavian countries. And say, well, you know, what was going on there? The other Scandinavian countries had far fewer deaths. Surely that's what you make the comparison with. Well, if you go on to the next slide, you'll see, yeah, again, you've got throughout April these growth curves, and you've got Denmark, and it's moving along in a similar way to Italy, the UK, and everything else. So in fact, until you get to the end of April, which is when lockdown measures might have started to have an impact on deaths, Denmark's on a similar growth path. So in fact, the fact you're getting more deaths in Sweden is not directly because of the not having a lockdown policy. There are other reasons why Sweden was having more deaths. It may have been policies for care homes. I don't know enough, but it's just really making the point that finding balanced growth, finding control groups which are on the same growth path is actually the crucial thing. So I think we can move on to the last slide now, Fernando. So what I've done here, I've gone through this whole new modeling framework that we've got for modeling epidemics, specifically coronavirus, COVID-19. And I've shown how it works forecasting in a univariate setup. And then I've gone on and I've looked at multivariate setups, and I've shown how it might be used to construct leading indicators and how it might be used for control groups to assess different policies. So I think there's lots of work, lots of interesting studies that can be done based on these newly developed techniques. So I think that's a good point at which to stop. Thank you very much.
Thank you very much, Professor Harvey.
Thank you, Andrew.
We have one question in the Q&A, and we have Nikos want to do a question for you as well. The Q&A one is for Skander Hanek. An intuition as to why the log of the growth rate is easier to model than the raw numbers over than the log acting to stabilize the variance.
Yeah, I mean, in a sense, it is stabilizing the variance. If you took the log of the daily numbers, that would partially work, but you've still got to put in the lagged total, and that's the crucial thing, and that's what, if you like, it puts a brake on the trend, and it's that pulls it down. The intuition is really coming from growth curve theory, that the growth curve theory tells you that the log of the growth rate should in fact go on a downward trend. So that's what the growth curve theory is telling you, and then from that you develop the stochastic model. So it's a combination of reasoning from deterministic growth curves and then combined with the statistics.
Okay, thank you. Nikos, do you want to talk?
Yeah, can you hear me? Yeah, perfect.
Yep.
Thanks a lot for the talk. I want to pick up a bit on the last part of the presentation, and perhaps easier to talk, that's why I asked for the microphone. I live myself in Sweden, you see, and I find the analysis quite interesting in the comparison because it's one of the ongoing discussions here, but in other countries as well. And my question essentially has two parts that I would like to have your comment. As you said in the previous slide, it's very difficult to find the control group, but my understanding, most of the comparisons I've seen, and I would argue partially in what you presented as well, is that we assume some sort of homogeneity between the different countries and different policies, health profiles. That's the one aspect that I wouldn't even know how to start, if you wish, estimating something on that. So I would be really interested to hear your views on that. And the second part is, shouldn't we have a bit of a more long-term perspective before we can be able to say if a lockdown policy was appropriate or not, or the nature of the lockdown, and as well a bit more multi-objective? Thanks.
Okay, thank you very much for those 2 points. The second one first. Should we be evaluating these? I mean, this is a first attempt at trying to evaluate these policies. Now you could clearly go into it in a lot more detail, but I think what I'm primarily interested in as a sort of statistician is developing the methods that can be used. And the methods I'm proposing are actually very different to, I think, what other people have done. I think the epidemiologists would tend to use their semi-mechanistic models and use simulation methods. But so what I'm providing is statistical methods, which we all know how to use, how to manage. The first question. Sorry, I've forgotten what the first question was now. Just remind me.
Yes, I can repeat. Sorry, it was a long question. Both of them were long together. The first question was essentially, most of the analysis I've seen, and I would argue up to a point, the analysis I saw here, though in the previous slide you actually claim the limitation as well, is that we assume some sort of homogeneity to be able to make this comparison.
Oh, okay. Yeah. I've got it. Yeah. I think this is the point that we're saying that when you do the looking at time series, what's important is they're on the same growth path. Now it doesn't matter that Italians are different from Swedes. The fact is, if the epidemic's on the same growth path, then you can make a comparison there.
Okay, thank you very much, Professor Harvey. Thank you, everyone. Should we move to Professor Esther's keynote? Thank you very much, for everyone. See you in the next one.
See you next year.
Hopefully.
The same computer.
Yeah, should we move to Rio? Bye-bye, everyone.
Bye.
See you.
Bye. Bye. Thank you.
Thank you.